Okay, so we're on section 2.2. Why is it doing that? Oh, thank you. We'll get this done eventually. Okay, so we did the triangles and the parallel lines the other day. That stuff is going to be helpful in what we're doing, those matching, but remember there was really only two sides when it was parallel lines with the diagonal cut through it. There was big and small. So don't stress about all the names. There was big and small. Figure that part out. So today we're going to talk about the types of triangles and some information with triangles. This first part is merely so you know what I'm talking about when I say different words, okay? It's not like I'm ever going to say, hey, what's the definition of this? But there are three different types of triangles as far as we're concerned. You've got the equilateral. Most of this is in your book too, and you can get the details there. But on equilateral, it has 3 equal sides in length. And same with the angles. There are 3 equal angles because there's 180 degrees divided by 3. That's where the 60 comes from. The side lengths are all the same, whatever that turns out to be. The other style is isosceles, which is not a word that you really walk around saying in your real life. But I probably will. So this is merely so you know what I'm talking about. An isosceles triangle has 2 equal sides and therefore 2 equal angles. It could be any proportion. I don't know what those 2 are. They could both be 40, both be 30, but it's got 2 different sides. And then the third style is called scaling. There eventually. There we go. And scaling is just a regular triangle. Okay. No equal sides. Okay, so that has to do mostly with the sides. Then there's 3 different ones that they talk about with respect to the angles. Okay, even that equilateral, I know that they're all 60, but concentration we're concerned with is really more about the sides. The other types of triangles are a right triangle. That's the one we'll do most of our work with. Not all of it, but most of it. So this is one we're going to slow down on just a little bit. A right triangle has one 90-degree angle. The way it's sketched, we'll have a little box down in the corner showing that those 2 sides are coming in perpendicular to each other. It doesn't matter where that box is or where that triangle is rotated, so it could come in, like this. But it'll definitely have that little box if it's a right triangle. It has a lot of special useful things, especially when we get into trig. So the right triangle is going to be our biggest emphasis. Okay, and then there's 2 other styles there. Not as important, the acute and obtuse. Whether it's an angle or a triangle, if you hear me say those words, acute and obtuse, an acute is just an angle less than 90 degrees, and obtuse is greater than 90 degrees. Okay, so again, not quite as big a deal, but the right triangle issue is huge. Okay. One of the things we can do if it's a right triangle, and only if it's a right triangle, is the Pythagorean theorem. Huge. Okay, looks like this. C squared, good, is equal to A squared plus B squared, or vice versa on that one. And that's coming from, my triangles usually look like this because in a trig class, that's the most useful orientation of it, but it doesn't matter where it's coming in. Okay, A and B are just the legs of the triangle, the 2 guys that are making up that 90-degree marker. Does not make any difference who's who, ever. Okay, so maybe this one is the A and this one is the B. Could switch those guys around, makes no difference. C, however, is important. C is the one that is opposite of the 90-degree angle. Okay, and your C gets a special name. C is the hypotenuse. Another word that you'll hear me say a lot. And if you just walk right through that little box to the other wall, that's always the hypotenuse. Okay, and again, A and B, doesn't matter who's who. Okay, so we're going to do just a little bit of work with that. Let's say we'll start off one. This is solve for C. Sometimes they'll tell you specifically the side. Sometimes they'll say the missing side. Just a little terminology difference. It's kind of obvious though, because you'll always have 2 out of 3. So here's my triangle. These are never drawn to scale. I have 2 shapes. That one and an isosceles where they're like 45-degree angles each time. It's only 2 shapes I usually draw. So this one we're going to say is 10 centimeters, and this one is 24 centimeters. And we want to solve for side C. Okay, now here's one of the things that went much better on the test. I was really happy to see this. But with your Pythagorean theorem, we've got C squared is equal to 24 squared plus 10 squared. Now, when you apply the square root sign, a couple things about that. If I apply the square root, because I want to undo this C squared, right? And the 2 exponent and this thing that sort of looks like a division bar is the square root. When I do that, I undo the power, so I get plain old C. And on the right-hand side, make sure when you type this into your calculator, you hit your square root key and a parentheses if it doesn't already give you one. And then start typing 24 squared plus 10 squared, and then close it. I haven't noticed this error with the TI-36X Pro, but some calculators, like the graphing ones, if there's other things in that memory that are in that stack dump and you don't close that, you can get an error that will be shocking to you because you're like, I did everything right, what's the problem? And it's merely because you didn't close it, it's got some ghost value, whatever they call it in there, okay? And then what's C in this case?
26.
So 26 centimeters. Okay. Now, that's how you do it when it's straightforward and it's the hypotenuse missing, because this really is something we're going to do a lot. We're going to do another example where it's one of the legs that's missing. So this one, we'll try and draw the triangle a little bit different. Right? So you're really just looking for that little box in the corner. And we're going to say that this side is 5 and this side is 18. And sometimes they won't put any units on it. This book is really better about that. Like in a regular trig class, they'll just go for the, it doesn't make any difference what the units are because they're always the same. But it could be anything. We'll give it one just for the heck of it as feet. And then we're going to find the missing side, B. Okay, so going back to the formula, we know A squared plus B squared equals C squared. I wrote this one in reverse on purpose. I don't want you to get locked into the fact that it has to be in this order with the C squared on the left. It's equality. That's a lot like a teeter-totter for a little kid. The equal sign is the middle of that teeter-totter, and those kids can get up and switch sides and still have a good time and then come back. So equality is either side. Okay, so I just switched it up on purpose, and I'll continually do that so you don't get locked into one version of it. All right, it'll make your trig section a lot easier. But then we're just going to fill in the blank. I don't know what B squared is, so 5 must be A. So I'm going to take 5 and square it equals C squared, which is 18 squared. Okay. Now, same thing, we're all of that algebra part, that part's still important. So I'm solving for the letter B, so I'm gonna have a B team and then everybody else. So this doesn't matter if I go to 25 now or later, it's still gotta subtract to the other side. Just in case that was a strange number like 3.74, there's no point in squaring these things up in advance. If they're tiny little whole numbers like you know it's a 25, then knock yourself out. But otherwise, just leave it in this form, it's faster for your calculator. So we're going to get B squared equals 18 squared minus 5 squared. Are you guys okay with that if I don't show my work on that stuff now? Okay, if you ever get lost because you're taking notes and listening and watching and trying to do all of those things at once, then just tell me and I'll go back and fill in the little missing steps.
So this is just, you can work it out as a regular algebra problem.
Exactly. Exactly. So now I've got a minus the 5 squared over. Now I'm going to take the square root of both sides. That part I probably always will show. And so plane B is the square root of 18 squared minus 5 squared. Now the last one I knew was going to come out to a cute little whole number. This one is probably not. Most of the time they'll have you stay with significant digits, but you'll notice this one's not. If they were going to go significant digits, this would have had to been a 5.0 or rounded up to a 20. So we're going to take this one to the nearest tenth, just randomly. Oh, look at that. Say it again.
17.3.
17.3, and we decided feet on this one. Okay, everybody doing okay with the calculator part of that, getting 17.3? Possibly, because it does little. I know. Want a hippopotamus for Christmas? Okay, so that's a big deal. The Pythagorean theorem, we're going to get our money's worth out of that deal. Then, the other things that we do, perimeter. Are we good with perimeters, just adding up the outside? Okay, so let's talk about area instead. Okay, there are 3 different ways to find the area of a triangle. One of them you're probably familiar with from growing up, and that is 1/2 the base times the height. Now, the only thing about that formula is that that height has to be perpendicular to the base. Everybody understand this notation? The height and the base have to be perpendicular to each other. So in a right triangle, this could be the height and that could be the base, or vice versa. It really doesn't matter. Base doesn't have to be on the bottom, right? Or we could have a picture like this, right? And so that's not 90 degrees. So they'll come in with a perpendicular this way. So this one, wherever that little red, or let's try that in English. Wherever the little X is, one of them is the base, and the other one is the height. But truly, this could have been the height, and that could have been the base. It's the 2 guys that are coming. Yes. Is that what you said? What is, or yeah, that is? What is? Oh, what is the height? I don't know.
No, I'm not saying the numbers, but what? Not the imaginary line that you drew.
Yeah.
Is that the height?
That's the height. And then this long line here would be the base. So those 2 pieces form a base and a height. Wherever the little right angle spot is, the perpendicular mark, is saying that I have 2 pieces, and wherever they meet, if there was a little box here showing a right angle, wherever those 2 guys are, one's the base and one's the height. But it doesn't, I can't rotate this whole thing. Maybe I can. Hold on. Yep. All right. Ooh, too many pieces. I don't think I can do that. Okay, if I could turn this whole unit as one, it saw it as too many different pieces of the puzzle, but if I could rotate that around so that this was kind of on the ground, then it would be the base instead. It doesn't, it's just the 2 right angle spots are the height and the base, wherever they meet at 90 degrees. Okay?
So that black line right there is meaningless? I mean, I don't understand that.
Let's draw a bigger one.
I know the imaginary.
Okay, let's say this base is 20, and that's the whole length, right? Okay, and let's say this might not actually form a true triangle because we're making it up on the go, but let's say that this is 8 and this is 15, and this would be, like, let's say 10. Okay, so you know the 3 sides of the triangle, 8, 15, and 20. And this vertical height, if I measured this guy out, would be 10. All right, now if I wanted to find the area of that picture, it's the 1/2 of 10 times 20, or 1/2 of 20 times 10. We didn't talk about this a lot during the earliest part, but multiplication is something called commutative. That means that order doesn't matter. 10 times 20 or 20 times 10, either way, it's 200. right? So the order of those guys doesn't make any difference. You get 200 no matter what. And then I want half of that product. So this area is 100 square units of whatever the unit was, feet, miles, inches, whatever. Okay?
I guess my question was, the 8 has nothing to do with height.
No, none, zero, zilch.
That little dotted
I
line.
misunderstood you earlier, and you're right, it has nothing to do with it. William?
That's just, that little dotted line is just showing you the highest point of the triangle.
Right. So if I would go to the top of that mountain and drop a plumb line down, where it would, the length of that plumb line as it hit the ground would be the perpendicular height. Yep. So the 8 and the 15, trivia. They could be there and not. Kind of. Yeah. To see if you're grabbing the right pieces of the puzzle. Yep. And those can even be on the outside. Let's say my triangle looked like this. Okay. So definitely no 90 degrees in this one. This one I actually have. This is 20 centimeters. And this is 16 centimeters. And this is 29.5. Right? Well, right now, I don't know what the perpendicular height is. And until we work on our trig stuff, you can't figure that out. But there's more to this picture that they will give you in chapter 2. They'll do a little outside perpendicular action, okay? And then put a number on that, in this case, 15.1 centimeters. Okay, now when I want to figure out the area, now check it out though, this line, this little dashed part is not part of it. I've just got the 20 of the actual base of the triangle. So this area is 1/2 of 20 times 15.1. The actual base of the triangle and its altitude. From the highest point, if you drop the plumb line down, how far is that? So, and again, doesn't matter the order here, either one's good. So that's going to be 151. Okay? So the quick shortcut to that is go find the little perpendicular mark, the 90-degree marker, and it's the 2 numbers tagged with that. Of the 4 numbers on the page, I want the 2 that tag this line, which is 15.1, tagging this spot right here, and 20. Yes, sir.
Later this will get more complicated, right?
Oh, yeah.
Taking out parts out, because that's just for a perfect square, isn't it?
Right.
Triangle.
Stop killing the confidence.
My evil smile. Like,
I was making sure, because I wasn't, I guess, I
now?
was reverting back to the days when it was like, you have to figure out this and then that.
Right.
He's smart. So
Right,
Yep.
he's already ahead of us. So
For example, oh, yeah, great lead in. For example,
I'm probably as smart as him when he was 6.
what if you know the 3 sides, but not the perpendicular?
That's later on, you said.
Yeah, it's later.
Okay. Jump in the gun.
Time has passed.
I see.
Okay, so in this, remember there's 3 ways. We're only going to learn 2 of them today. The third one's going to wait till we get into trig. So if we don't know that actual altitude or perpendicular height, but we do know the 3 sides, then we're going to use Heron's formula. Every once in a while you'll see that without the N. You'll just see Hero's formula. Just doesn't make any difference to your learning, but just in case you ever looked it up on the internet, occasionally the N is not included. If that, okay, Heron's formula says that we can find the area of a triangle. We're not going to do the proof on this one. I'm just going to give it to you. The area of a triangle is equal to the square root of S times S minus A times S minus B times S minus C. So A and B and C are the 3 sides of the triangle. Works for a right triangle, obtuse, scalene, equilateral. You pick one, it's going to work. Okay? But what the heck is S? Right? We know ABCs are the sides. So S is 1/2 the sum of the sides. A plus B plus C, add them up, cut it in half. We're going to do our first example of this with one where it was unnecessary. We actually knew the perpendicular height and the base, but it's tiny numbers and it works out to whole numbers, so it's convenient. So we're going to go this way, okay?
I don't
I'm
want
hanging.
to be later anymore. I want to go back to then.
No, this one's not bad. It's long, but it's not bad. Okay. Okay, ready? So here's a triangle for you. And this is 5, and the base is 12, and the hypotenuse is 13. Okay? And we are going to find the area of this triangle. Now, as it turns out, I'm not going to write this on the board, but as it turns out, this is actually perpendicular. This is one of the special right triangles. Okay, but we'll do that part secondarily. If I was going to use Heron's formula, first thing I do is go find little s. Reminds me of kindergarten too. Little s and big S. So we're going to have half the sum of the sides. So half of 12 plus 5 plus 13. So 25, 30, cut that in half and get 15. Pretty good so far? And addition is also commutative, so the order that I pick those totally doesn't matter. Just add up 3 sides, whatever that total is, cut it in half. So I'm going to play with the number 15. Okay? Now, Heron's formula says the area is equal to the square root of, okay, it's 15 times 15 minus a. Okay, let me pop back to the other page for a second. Multiplication is also commutative. Order doesn't matter. So did it matter if I said A and then B and then C? I could have said C and then B and then A. I just need you to take S and 3 times subtract the side from it and also the original. Okay? So there's 4 numbers inside of this. So back on our example, we're going to have 15, and I'm just going to take them in the order I happen to write them up here. 15 minus 12, and then 15 minus 5, and then 15 minus 13. Okay? It's long. There's no getting around that. For real, it's long, right? But, and this one's nice, pretty little whole numbers, so I'm going to continue part of this on the board. If you had a calculator, you could just type your little heart out. Okay? Don't forget there's a gigantic parentheses, or calculate this and then take the square root of your answer. It's usually safer. So, for me, or hand do a little bit of it. So I'm going to have 15 times 13, or how about 3 instead? 15 times 3. And then times 10. And then times 2. I don't know what 15 times 60 is. Tell me what the answer is here. 900? 900? And again, that's square units of whatever our units were, because it's area. I'm just going to say units squared for now. You got 30? Oh, did you not take, oh, it's square root of 900?
Square root, yeah.
Okay.
Yeah, it's
We can fix that, no worries. Thought that was really big, but. Okay, 30, so the square units piece needs to come down here. Come on. Oh, you're not going to do that. There you go. Okay, so it's just plug and chug. It's a lot of plugging and a lot of chugging, but the formula is not horrible. Add up the sides, cut it in half. And then you have that number, and that number minus all 3 sides. Okay, so did anybody just type it in right at this top row?
I did.
It's not that big a deal, is it? No. Is that the calculator I should go, or do you use that one? Use that one? Okay, so this particular triangle that we used is actually one of, like I said, one of the special right triangles. Special. And as it turns out, which we'll worry about again more in the trig chapter, but if this is 5 and this is 12, you could do the Pythagorean theorem to prove to yourself this is 13. Those actually met at a right angle. That was not on the previous picture on purpose because it works for any triangle, right? It doesn't matter. But since this one is coming in at a right angle, my area could have gone back, if I'd known that, to just 1/2 base times height, right? So I wanted to use one where you could kind of check your work. So if I consider the base to be 12 and the height to be 5, there's your same 30. So obviously quicker if you know the perpendicular base and height. Obviously, a lot less work. But if you don't, you can still find the area. The third way, we're not going to worry about just yet. Okay? We're going to get through 3 sections or 4 sections in the next 2 days, so we're moving on. But that's the end of the area stuff for the triangles. Right? I'll split that up. Okay. So in section 2.4, the PDF will be saved separately for 2.4. We're going to talk about quadrilaterals. Oh, shoot. Yes, 2.3. I got something special I have to tell you about 2.4, but don't, that I thought was today. Okay, quadrilateral means that it has 4 sides. And there's a lot of different categories, and we're not going to spend a lot of time on that. So please, in your book, take a look at it. There's a parallelogram, a rectangle, a rhombus, a square, a trapezoid. Okay. For those top 4, the parallelogram, for everything except the trapezoid, the area is base times height, like your rectangles, your parallelograms. The trick to that, again, is that that height has to be perpendicular to the base. It might show it on a parallelogram inside. Does everybody know what a parallelogram is? I guess we should go back to that. Okay, parallelogram is a box that somebody pushed on its side. It didn't have a support to it. Okay, that's parallelogram. I'm just going to put a P with that. A rectangle is the box that has not fallen yet. Those are all coming in at right angles, all 4 of them. So here, base and height would be easy because they've got to be the sides. They're all coming in perpendicular. Here, somebody slid it. So if I wanted to find the height, either inside or outside, somebody would have to tell me the height. Yeah?
What's the difference other than the length of that parallelogram and the rhombus?
Nothing except the length.
Nothing except the
That's
length.
it. A rhombus is a square. Whoops. A rhombus is a square that's fallen. That kind of looks like a square that's fallen. Like it just didn't have those corner supports, so the box is leaning. And a square is all 4 sides are the same length, and everybody's coming in perpendicular to each other, right? So this is a rhombus. Not a word we use a lot, but that's still what it is, the square. The whole back in geometry, you know, as a parallelogram is a rectangle, parallelogram, which one's true, and the converse, and we're not even going to go there, okay? Those are just the 4 shapes in case we happen to say them for which one's which. There is one other quadrilateral, though, that does not work for this, base times height. Same thing on the rhombus. It's just all 4 sides are the same, but it's still just a little parallelogram, right? It's a specific kind. This is still a rectangle. It's just a specific kind because it's got all 4 sides the same. But the trapezoid, trapezoid always reminds me of that little circus thing that the elephant stands on. Because it's got 2 parallel sides and 2 that aren't. But it's still a 4-sided object, so it's still a quadrilateral. So this time, because my base and height is a little bit different, my height's the same. These guys are parallel. We're going to call them B1 and B2. Clever, eh? Doesn't matter who's 1 and who's 2. In order to find the area this time, you're going to find that average length of the base. So you add them up and cut it in half, that B1 and B2, times the perpendicular height, and that still has to be perpendicular wherever they decide to tell you. Inside, outside, wherever, it's still a perpendicular height. Okay? But instead of just like length times width, we say base times height in math, but like in, if you're actually finding the area of the floor, it's length times width. That's 1 is the base and 1 is the height. Just multiply the sides. That's all we do. Okay. So this one, we're going to do a really quick example of this. Really quick. Okay. We're going to take this parallelogram and find the perimeter and area. Perimeter on the triangle, but it's the same theory. We're just going to have an extra side here. And here's my parallelogram. Okay, looks like that. And this diagonal is 2.5 meters. And the base is 3.2 meters. And the perpendicular height is 1.8 meters. Okay, so those are all the bits of information that you get. So if we wanted to find the perimeter, right, in a rectangle, you'd usually say 2 times the length and 2 times the width. Here, we're going to get 2 times the base and 2 times the diagonal. You could just actually physically walk them off too. 3.2 plus 2.5 plus another 3.2 plus another 2.5. Whatever works for you. On a trapezoid, you'd have to do that because they wouldn't have to be the same. So you're going to add those up. Survey says 11.4. No, I think it is 11.4. Yeah, because the times 2 is already in there. Now, if it's perimeter, it's a linear measurement, so that would be just meters. If it's an area, that's 1/2 the base times the height, right? And it's the perpendicular height. So the base we'll say is 3.2, okay, and the height is the perpendicular 1.8. Here it does matter who's the base. It's where the right angle meets. So the 2.5 is not part of the 90-degree marker, so I can't use that number, okay? So survey says their last one, so 2.88. Right, and this one would be meters squared for area. You're probably fine with this, but I just don't know if you've ever thought about what's the difference between meters squared, and meters cubed. Why do they put those units on the back end? If it's a linear measurement, I'm just measuring from here to there, it's a straight line. It only has one dimension. If it's an area, it's a paintable space. Right, so that's a 2-dimensional, like a flat wall. This is all being done in 2 dimensions. So it's meters squared. And it has a length and a width. This just had a length. Right? And if it was a box of some sort, then it would have a length and a width and a height. So it has 3 dimensions. So that's why volume is meters cubed. I don't really have a thing. Length, maybe? Not a big deal, but if you get that it's how many dimensions are you measuring in? Are you in 3D or 2D? Then it kind of helps you get the right unit at the back end. Okay? Tomorrow, if you own a TI-36X Pro, I need it in this room tomorrow. Okay, I don't even care if you bring your book, but bring the TI-36X Pro. If you do not own that particular calculator, bring whatever you're using. But if you're running 2 of them, this is it, the TI-36X Pro. If you own this specific calculator, I need it in this room tomorrow. There is an error in the programming where you will get a wrong answer when you type something in that has to do with the area of a circle. And I need them here so we can overcome that error, because telling you that that's what your calculator said will get you fired. Okay? It's a huge error. So we need to get that. They can't patch it though because it doesn't have a USB connector of any type, and they're on the market, and why they're even still on the market is beyond me. Listen, amazing. Other than this flaw, it's amazing. But this flaw is huge. It's enough to get a person fired or to ruin a building or anything that has to do with the area of circle. It's huge. So it has to be here tomorrow so I can teach you how to overcome it. Because once you know it's a flaw, you just go, oh yeah, okay, no big deal. Right? But if you didn't know that that was wrong, wow, you would get wrong answer by a multiple of over 3. Okay. Cool? Are we good? All right. Love you, miss you. Bye.
Well, then once you combine it